Today I'm going to be making ethyl iodide, a strong alkylating agent which I'm going to use in a future video to turn Tylenol into dulcin, which is an artificial sweetener. To begin, I add 100 ml of ethanol to a round bottom flask, followed by 10 ml of water. I then turn on the stirring and add 40 grams of iodine. A few minutes later, the iodine fully dissolved. At this point, I add 5 drops of concentrated hydrochloric acid. I then place the mixture in an ice bath and let it stir for a while until everything cools down. Once everything is nice and cold, I slowly add 5 grams of crushed up aluminum foil. Once all the aluminum was added, I add a condenser on top of the round bottom flask and turn on the hot plate to heat up the water bath. It may take a while for the reaction to start, but eventually you'll start seeing bubbles form. So, to recap, in the mixture there is ethanol, water, hydrochloric acid, iodine, and aluminum. Here's what's going on. In the first step of the reaction, the hydrochloric acid reacts with aluminum's protective oxide layer, exposing aluminum metal to the solution. The aluminum then reacts with the iodine to form aluminum triiodide. The aluminum triiodide then hydrolyzes in the water that we added to form hydroiodic acid. The hydroiodic acid reacts with the ethanol to form ethyl iodide. This is what it looks like after 1 hour of refluxing. You may have noticed that there is less aluminum than when we started. After an hour and a half of refluxing, almost all of the aluminum is gone. At this point, I add another gram of aluminum just for good measure. It's now been 2 hours, and the reaction is mostly over. As you can see, there is almost no unreacted iodine left. When there was still iodine, the color of the solution had a dark purple tint. Now it became brownish green. I don't know where the green comes from, but it's maybe some impurity or side product. At this point, I turn off the stirring and replace the hot water bath with a cold water bath to let everything cool down quickly. I then filter the mixture through some cotton and sea light. The filtrate passing through was completely clear, which means that all of the iodine had reacted. Unfortunately, this didn't last for long, and eventually some yellow color started passing through. Eventually, the filtrate turned red, which is a pretty bad sign, and this means that the ethyl iodide is starting to decompose and release iodine. Ethyl iodide is quite light sensitive and air sensitive, so since I'm filtering it through sea light, it's a pretty slow filtration, and a lot of the ethyl iodide is degrading. Once the filtration is over, you can see that it turned brown. This indicates the high iodine content. I then assemble a distillation apparatus and distill off all the liquid. Eventually, I started getting some drops of distillate. I looked at the temperature and I noticed that the temperature was 79 degrees Celsius. This kind of bamboozled me a bit, since ethyl iodide's boiling point is 72 degrees Celsius, and 79 degrees Celsius is much closer to ethanol's boiling point. At first I thought I had failed and that I didn't actually make any ethyl iodide, but then I realized that the solution was very dark brown, indicating a high iodine content. And since iodine impurities tend to raise the boiling point a lot, this is probably all the ethyl iodide coming off. For example, if you have a solution of iodine in ethanol, ethanol's boiling point is normally 78 C, but all the iodine can raise the boiling point to over 85 C. This makes the distillation a bit confusing since it's hard to determine which liquid is boiling off. Anyways, in the end I collected around 90 ml of distillate. This is mostly ethanol, and all the ethyl iodide is in here. To separate the ethyl iodide, I dump the whole mixture into 350 ml of ice-cold water. Ethyl iodide is insoluble in water, and it will form a separate layer at the bottom since it's twice as dense as water. As you can see, we have some dark red liquid sitting at the bottom of the water. Ethyl iodide is colorless, and the red color comes from all the iodine. I then decant the upper aqueous layer and get everything into a smaller beaker. As you can see, there's a very small amount of ethyl iodide, and it's much less than I expected. This reaction is very inefficient, but I didn't think it would be this inefficient. To get rid of the red color, I add some sodium thiosulfate solution. When I stir it around, the sodium thiosulfate reduces the iodine into sodium iodide, which dissolves into the aqueous layer. I then pour off everything into a separatory funnel and drain off the organic layer. The aqueous layer was then drained into a separate beaker. This can be disposed of. I then add my ethyl iodide back into the separatory funnel, followed by some saturated sodium chloride solution. The ethyl iodide is probably still a bit wet, and the sodium chloride solution helps dry it. I swirl around the separatory funnel to mix the two layers, and then let it stand for the layers to separate. I again drained off the ethyl iodide into a measuring cylinder, and as you can see, we were left with around 1 milliliter of ethyl iodide. This yield is an amazing 4% yield, which is extremely ridiculous. I really have no idea why the yield was so low, but it was probably because a lot of the ethyl iodide decomposed, because there is a lot of light here, and it's also quite warm, and it was exposed to air for a long time. This process is very inefficient, but after all, it is the only way to make ethyl iodide without red phosphorus. If you have access to red phosphorus, then of course you need to use red phosphorus if you don't want to have a 4% yield, which is absolutely ridiculous. But if you really don't have red phosphorus, then this method is feasible if you need small amounts of ethyl iodide. Anyways, this project was disappointing to say the least, but hey, shit happens.